Initially, I wanted to create a tutorial how to synthesize an internal combustion engine sound, as I made a cross-plane V8 sound for the car Snake in Succore's game. In the process of creating this tutorial, I realized that the amount of information is too large and it would be better to split it into two parts. You can subscribe to stay tuned, I'll do the second part of the lesson next time. Therefore, I will dedicate this tutorial to the fundamentals of sound synthesizing using C++ and SDL. SDL is not necessary to understand sound synth basics. We can just write a wave file as an output. But using SDL, we will be able to hear the sound immediately when the program starts and change sound parameters in real time later. SDL, Simple Direct Media Layer, is a cross-platform library used for handling graphics, sound input, and window management. I will use Linux as it is easy to deploy C++ project with libraries, but shortly for Windows. Go here on GitHub, select Visual Studio version, and download SDL include and binaries. Find SDL2 in the bottom. Deploying Sound Synth project in SDL3 was unfamiliar to me, and I considered it is unnecessary to spend more than half an hour on it. Download, extract, set up environment path to SDL2 DLL. Create a console C++ project. Right mouse button on project name properties. Set up include and library paths. Set specific libraries in linker input. Include SDL, not SDL2 SDL. Volume down, build, and listen to the 5 seconds beep sound. Back to Linux. IDE, qtcreator, build system, cmake, compiler, G++. The only external library is SDL with SDL mixer. That's all what we need. Create a blank C++ project. Create project, green button on the left, select plain C++ application. Name it something like SDL sound tutorial. Select cmake. Select release and debug options as we don't need any other. Add version control git and press finish. If you create a project outside of the home directory, you get an error from git version control. We'll fix it in a couple of seconds. Now we can see this awesome Hello World application code. To fix version control error, select the terminal in the bottom of the window, type git status, copy and paste this add save directory line. Type again git status, and it seems it works. Add untracked files, make initial commit, run the program, press Ctrl R, see Hello World, it's time to celebrate. Let's ask any language model service to create a simple sound synth example with SDL2. Copy and paste in the IDE this code. Code parser doesn't see any error, no red underlines. Let's compile it, Ctrl B. As you can see, there are many undefined reference errors. Let's fix them. Add target link libraries to link SDL and SDL mixer libraries. Please lower the sound volume. The sound wave might be too loud compared to this video. Run the program, Ctrl R, and enjoy the sound wave for 5 seconds. Celebrate it! Before we move on, let's commit what we have already done and figure out what is going on here. I refactored a code to make it more readable. First of all, what is sample rate? It is how many samples of wave there will be in 1 second. 44,100 Hz is historical standard for CD audio and it is common. Another common sample rate is 48,000 Hz. It is used in Unreal Engine, by the way. The higher sample rate is generally imperceptible to most people, which means there is no reason to increase the CPU load. Synth data is structured with constant phase increment for the sine wave. On each step, the phase will be incremented with the phase increment in audio callback. Phase increment is the frequency divided by sample rate. For the sine wave, we use angular frequency, so we should multiply it by 2π. The main thing is this audio callback. It generates a wave. The audio callback function is executed near 44 times per second at this sample rate, and fills 1024 samples of waveform position. You can see a for loop here. This function is executed on a separate thread. It is important to remember. Parameters. User data is a synth data itself that we set inside the main function. Retrieve here and reinterpret it back to the synth data type. Stream is a byte array. We reinterpret it as 16-bit signed integer as we set audio as 16 Cs in desired params. Len is the size of audio buffer array in bytes. As we set 1024 samples and format is as16 Cs, 2 bytes, the size will be 1024 times 2 equals 2048. Inside a callback, we calculate num samples back dividing by byte array lengths by 2 and get 1024 samples. And now our task is to fill this array with the sine wave samples inside this for loop. First of all, we calculate a wave itself. We get a sine wave from phase and multiply it by 0.3 to decrease volume. Fill the current sample in a buffer with the wave. As the wave is signed 16-bit integer, we multiply a float value to 32,767. It is a max value of 16-bit signed integer value, and cast it to 16-bit integer. To avoid integer overflow, we should clamp the wave, the function above. If the wave exceeds 32,767 without clamp, the number wraps around to the minimum possible value. In sound generation, it can cause very sharp noise artifact, so it is better to clamp. The next step is necessary as well, to update wave phase. Add phase increment to it. Since the precision of floating point number quickly degrades, the increment value can be below size of floating point error and will no longer increment. So it is better to keep the phase within the range of one wavelength. For a sine wave, it is 2 pi. Let's use fmod function for this. It returns a remainder of division operation, from 2 pi in our case. Inside the main function, there are SDL audio initialization. If can't initialize, close the program. Adjust audio parameters. Logic audio device initialization. On-pause the device. Wait for 1 second. After 1 second, we close audio device and quit SDL. Let's commit it. Oscillations. Let's write a class with a basic set of oscillation functions. Sine, triangle, saw, square, noise. Each of them, except noise function, updates a phase. The phase starts increasing from 0 and exceeding 1, a phase value resets to its fractional part. So fract of 1.04 is 004. So calling a gen function, it updates a phase and returns a wave function from phase. Phase increment parameter is frequency scaled by inverse sample rate. Take a look at our audio callback function now. First of all, look at ISR. It is inverse sample rate, or time delta of each iteration step. GenSine now generates a wave, take frequency scaled by inverse sample rate, and makes a phase offset inside the OSC instance. Let's commit it. We can combine waves as well. Let's add a low frequency oscillation. Our sine wave now multiplies by low frequency triangle wave. Let's multiply a sine wave by normalized 0 to 1 square wave. We can also make frequency oscillation, so we add the triangle wave function to the frequency value. The next important thing is to make a low-pass filter. To create the low-pass filter, we make a linear interpolation function lerp. Lerp is the function that calculates a value partway between two known values. Result is the transition between A and B with value x in range 0 to 1. We will use the lerp function to smooth the wave. The smooth wave is the mix of current and previously stored wave position. If x approaches 0, the result tends to remain unchanged. If x approaches 1, the result tends to be the same as the wave. By changing x, we can adjust the rate at which function changes. Let's take a look to the square waveform and listen to it. Look at the smooth result wave. To create a high-pass filter, we need to subtract the low-pass filter result from the input wave. You can see the sharp spikes, it is a high-frequency filtered result. We can smooth a noise function and apply it to the frequency. The tire noise in the game is based on this technique. Well, this tutorial is about 10 minutes now. So let's save the internal combustion engine sound generation part to the next video. Please like, subscribe, so you don't miss the next tutorial. You can support the game development buying the Sucrace game on Steam. That's all for today. Have a good day. Goodbye.